Good morning. So it keeps slipping my mind. I keep forgetting to ask you guys to do my evaluation. So every term teachers get picked to do evaluations. And so I have been kind of assuming that you've been getting emails from the college reminding you to do them, but I have no idea if that's the case or not. So just to show you, we have some important stuff to cover today, so I'm not going to give you any time to work through it, but I'm going to show you where to find it. So if I go to my Moodle dashboard, then it might be one of the blocks. I just have a select few blocks showing, but over on the left-hand side, or at least on mine, I have this formative evaluation of college professor. So if you click there, then you read the instructions, of course. It says it's going to take 25 minutes. I have no idea why it would take you 25 minutes unless you're writing some sort of essay. You don't need to do that. But the reason that I am a little bit panicked about it is because it closes on Friday. Oh my gosh. And I've been forgetting to mention it, but anyways, doesn't matter. So there's the survey link for the fall. So we're in the fall term. So if you click that, I'm just going to show you what it's going to look like. And then of course you read and great. And then you hit next. And then you're going to choose me from the list. Go down to the Lees here. And then you pick, so this is a cross-listed course, of course. So so if you're in the biology section, then you pick the biology 202. And then if you're not, if you're in stat 230, you pick stat 230. So let's just pretend that we're in stat 230. And then you can hit next. I just want to point out, just so it isn't so overwhelming. I mean, it looks like a lot of questions, but they're all pretty straightforward. The only ones I really care about, and the college cares about, are these strongly agree to strongly disagree or not applicable ones. So basically these multiple choice questions. So if you scroll down, blah, 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 it looks like a lot of questions. And then there's these open-ended answers. You don't have to submit anything there. It's just if you have something to tell me. I always felt like I had to come up with something and that would take some time. But if you don't have anything that you want to add there, you don't have to. You can just skip that. So like I said, it's really just these multiple choice, the bubble portion that I care about and the college cares about, my bosses care about. Okay, so if you wouldn't mind doing that, that would be awesome. And I would really appreciate it. Okay. So, please, do my evaluation. It closes on Friday. I never saw what time it closes. But if you could take a little bit of time, it's possible that you have to do it for more than one of your teachers. So usually you have to do it for all of them. So you've probably done it before, but if you could do mine, that would be great. And if you have already, then thank you. Okay, so good. Check. Can check that off my list. So we were talking about regression, but I was also talking about test one. So I'm still marking the long answers. And so, but those 13 marks are still, they're already incorporated into the 65. So I'm going to top that up. Okay, so your grade can only go up from what you got. Okay, so until I've marked the long answer, then you won't really know what your test 2 grade is. So I know you're waiting for me, but they're so long. You guys did them, you know how long they are. And then read 30 of them. Nice. Anyways, so, but so far so good, so that's great. All right. I think that was all for administrative stuff. Okay. Pretty sure. I feel like I'm forgetting something, but I don't know. All right. So for a little bit of review, okay, we started talking about regression. Regression is really just the line of best fit. All right, so we talked about, okay, we're going to have some response variable on our y-axis, and then we're going to have some explanatory variable on our x-axis, and then we're going to try to model the relationship. Okay, and so we will use a linear model. Oops. A linear model to model a straight line relationship. Okay, so to model a straight line relationship. Okay, and I'm going to underline this because kind of redundant. When I say linear, I mean it's a straight line. Okay. So what we're going to have is, recall from kind of high school maybe, or I don't know, whenever you saw y equals mx plus b, hopefully it wasn't too long ago, but maybe y equals mx plus b is the equation of is a typical equation that we use for a straight line. Okay. So this here is an equation, or I'll say a typical equation for a straight line. Okay. So what we said last day and what we kind of ended on, so I'll end that review and start calling this new stuff, is that, okay, we're going to have some population model. So there is some population model, just like we had the sample mean, and then we were able to do inference about the population mean, right? So now we have some sample model that we're going to use as an estimate for the population model. Okay, so what we're doing is we're really going to be modeling y equals beta naught plus beta 1 x plus some error term. Okay, but the betas, we never really use them because this is the model. This is a linear model for the population. Okay, and just as a side note, this is the error term, but we're going to ignore that. So I'm not going to go deeper into that, but it's there, but we can ignore it. Okay, so what we will do, so just like with other inference that we've done, oops, other inference we have done, we will estimate this population model using a sample information. We will estimate this population model using sample information. Oops. My hands all, sorry. My writing is usually really bad, but today, I don't know, my hands all messed up. Or maybe I'm just sloppy. There, maybe a little bit of both. Okay. So we use sample information, and so what we get is we get some y hat, which is the predicted value of y. Okay, and we talked about that hat before. And so context is going to tell us, okay, a p hat, that's a sample proportion, a y hat, now we're in regression, and I'm predicting the y. Y hat is b0 plus b1 x. Okay, where of course b0 or b naught, right? If we have a subscript 0, we usually use naught, right? So b naught is the intercept, right? It's the y-intercept, and b1 is the slope. Okay, notice we've got, instead of beta naught, we have b naught, and instead of beta 1, we have b1, right? So we're using these estimates for the model. Okay, so this is the model that we're going to build. Okay. So here, y hat is the predicted value of y. Okay. B naught is the y-intercept. B1 is the slope, because it's attached to the x. Right, so whatever's attached to the x, you could use a's and b's if you want. I'm going to use b0s and b1s, but you can use a plus bx, or even if you want to get weird, I don't know why you would, but you could use b plus ax. It doesn't matter, right? Whatever's attached to the x is the slope. Whatever is attached to the x is the slope. Okay. Okay. So that's great. Now the goal is to predict values of y. We're going to have some unseen value of x, or potentially seen, but what we want to do is we want to predict the outcome, right? So we want to predict y. Okay, so the goal, the main goal, there are other things we can do, but the main goal of regression, right? So fitting this model, or finding the model, is to predict values of y. Okay. So what we need is ways to be able to find the slope and find the intercept. Okay, once we've calculated those, then it's just a matter of, okay, I give you a value of x and you can predict the value of y. Okay. So, for example, if I tell you that y hat is 3 plus 2x, and then say, what is the predicted value of y when x is 4? What is the predicted value of y when x is 4? The questions are going to have this layout. It won't feel like it, because usually we have some variable name for y and some variable name for x, right? So what is the predicted sales when the amount of material you have is 4, right? And so it doesn't read as easily as this, but you have to keep track of what your variables are, and then it will have this kind of simple style of question. Okay, so it won't look this simple because we'll have values, or we'll have variable names for x and y. Okay, but what we're going to do here is, and I'm going to try to keep it on this page here, y hat is 3 plus 2 times 4, which hopefully puts me at 11. Now I'm going to keep it on here because I've got a page break. And because I hate running, I hate seeing equal signs run across the page, it just drives me nuts. I'm going to bump it up and stack my equal signs properly. So then my predicted value of y would be 11. Okay, we can figure out what this would look like, but we should be using software to draw this. So pretty old school stuff. We used to make you, and drove me nuts too, used to make you draw these lines that seem so stupid because we have computers that can draw these lines, right? But you would draw your intercept and then you'd find another point on the line. Once you have 2 points on the line, you can connect them with a straight edge and draw your line, right? And so, but we're not going to do that. We're going to use software if we have to. Considering it's our last day of material, we've got more important things to focus on. Okay, so let's see here. So the whole goal is to predict values of y, okay? And so we're going to have a slope and an intercept. It is going to be important that we know how to interpret the slope and the intercept. And so from those notes that I posted, I have the interpretations here. Okay, so here, if you need, and they're on the formula sheet too, but if you need to calculate the slope and then the intercept by hand, if you have this core information, then you can. But what I'm going to focus on is I'm going to give you output, and we need to look at it and build the model from the output. So there is going to be practice using these equations on the assignment, but on the final exam, I'm going to give you output and potentially I'll see how you guys do on the assignment. And it's typically, not that bad. And I'm going to give you some a practice problem. Okay. But what's not in the notes here, that's what I want to talk about. Okay. So I'll give you an example. You're expected to know how to calculate the slope and the intercept given these pieces of information. Okay. But first, let's talk about how to interpret things. Okay. So the slope, we calculate the slope first. Okay. And so in y hat equals beta naught or b naught plus b1x, we calculate the slope first. Okay, so even though you might want to calculate B0 first, well, B0 requires the slope. Whee. Okay. So that's why you have to start with calculating the slope and then you can find the intercept. And I do want to pull in, from that formula sheet that you have. All right, a nice little summary. So here's your least squares regression line, B0 plus B1x, just outlining what the format would be, and then with the slope. So I tell you that this is the slope, and here is how we calculate it, right? It's the correlation times the standard deviation of the y's divided by the standard deviation of the x's, and the y-intercept is going to be the mean of the y's minus the slope times the mean of the x's. Okay. So in terms of the slope, if we think about it in here, right? If we have to interpret the slope, and the interpretation of the slope is always the same. So in general, it says for each unit increase in x, okay, whatever x is, we will see a slope increase in the predicted value of y. Okay, so if we pretend that B naught is just held steady, let's make it 1 just for simplicity's sake. Or I guess we can make it 0, make it even easier, right? So then if the slope is, so just for example, where can I put this? Maybe here. For the slope, right, if I've got y hat equals 0 plus 4x, right, what we're saying is that, okay, the predicted value of y when x is 1 would be 4, right? So at x equals 1, y hat equals 4. So then for each unit increase in x, so if I make a unit increase in x to 2, then what do I get? Then I get my 4 times 2 is my predicted value of y. So then y hat would be 8, right? So this is a 4-unit increase. Okay, and this is a 1-unit increase. So you can really rely on the setup of the formula, right, or the model to help you with the interpretations, right? So for each unit increase in x, we'll see a slope increase in the predicted value of y. Okay. What about the intercept? The key part about the intercept, so the intercept here is b0, right? And how do we interpret the intercept? Well, the intercept is the predicted value of y when x is 0, right? And so, for example, let's see here, the intercept y hat equals, I don't know, 3 plus 2x, okay? At x equals 0, y hat equals 3, which is the intercept, right? And so that gives us the definition or the interpretation of the intercept. So the intercept is the predicted value of y when x is 0. So it's really important that we say this when x is 0. Okay. Good. So you will have to do those calculations. You'll have some practice on the assignments, but there's also some output that you need to see. But I think I have one more thing I want to talk about before, or 2 more things before we can talk about some output. Okay, so our goal is to use the regression line. So we want to use this line to predict values. Great. Okay. The problem is, and there are lots of examples where it becomes a real problem when we're trying to predict values of x, so 4 values of x that are outside the range of our data. So remember, we built our model based off of this range of x, whatever our x's are in our data. Okay. And so when we try to predict values of using values of x that are outside the original data, then we are extrapolating. Okay. And so if you're predicting inside the range of the data, it's called interpolating. That's not a concern, right? But the problem becomes when we're extrapolating beyond the range of the data. Okay. So the problem is that we only know the behavior within this range of x that I've built my line on. Okay, and so if we try to extend this line, and kind of the downfall of straight lines is that they do extend to negative infinity and positive infinity, right? So lines just keep going and going and going and going. You can use a line to predict for any value of x, but what we need to do is we need to say, okay, whoa, I didn't actually use these values of x for my predictions. So what happens? What happens then? It's still going to be our best guess. Okay. But that doesn't mean that it's a good guess. Okay. So, for example, if we look at this percentage in poverty data again, right, then our values of x were between, let's say, here 75-ish, and let's say 95-ish. I need a smaller pencil here so you can see. Clean that up. So we built this line using x's between 75 and 95, and in this case it's percent. Oops. Uh-oh, now I've done it. Where can I touch so it doesn't all go to spoils? There. Okay, so now we're allowed to use this line, and we feel comfortable using this line, and that's what we're going to do. We're going to use this line, but we should restrict our predictions to stay within 75 and 95%. Now, going back to the definition of the intercept, right? The intercept is the predicted value of y. So in this case, it's going to be the predicted percentage in poverty when x is 0. But notice that 0 is not within our range here. So what happens is the intercept is an extrapolation, and that's often the case, right? So 0 is not necessarily always a part of our data, but we need somewhere to anchor the line, right? We need somewhere that it passes through the y-intercept. So often what we're going to find is that the intercept is an extrapolation. Okay, it is still the predicted value of y when x is 0, but we might have to follow it up and say with, well, it's not really that interesting because it's an extrapolation. So we don't feel comfortable using it as a prediction. Okay. So here I'll say the intercept is often an extrapolation. So sometimes we'll have the advantage of knowing something about the data, right? Knowing that it would continue to be linear, or knowing that it would plateau. Okay, so for example, if we have data on a child's growth between the ages of 3 and 8, we understand that, okay, we keep growing, but then we hit some age and then we kind of stop growing, right? We stop growing, and then at some point we I don't know, somehow shrink. Poor posture maybe, right? And so I feel like I used to be taller, but anyways, so we understand, we have this knowledge about the data. Now that's an advantage, right? Knowing how the data would behave so that we can check our model against it. Usually that's not the case, right? Usually that's the reason that we're analyzing things, is because we don't know what's going on, right? So in this case, if we think about it, then we have data on the height, I think. Yeah. Between the ages of 3 and 8. We expect this straight linear relationship, you're continually growing, and there might be some ups and downs, but in general, we've got this upward trend. Okay. And so you're going to find a strong linear relationship between the age of the child and the height of the child. Okay. And so what you're going to do is you're going to fit a regression line, and you're going to say, great, okay, now I can make predictions. Okay. And so what are you going to do? You can predict how tall this person's going to be at 25 years old. But we know, I can't remember when you stop growing, but probably like around 18. So you don't keep going to 25, right? Which the line would let us do. So if you're just blindly plugging things into the line, then you're going to get wrong predictions, or at least unreliable predictions. Okay, so here, since this is an extrapolation, it is an unreliable prediction. Okay. Good. I think I had some other fun ones. You can even have, I'm kind of done talking about extrapolation, but this one's pretty interesting. So sometimes, depending on what section of X you're in, right? So here we have information on the men's age at first marriage, so how old they were when they first got married, and then by the year. So this would be what we call a time series. Okay, so when X is a time variable, okay, so that can be year, it can be minutes, it can be hours, whatever, months. We call this a time series. Time series analysis is its own beast. Okay, so it would be its own course. Dealing with time series, there are lots of methods that we have that we can use, but just be aware that when you have time on the x-axis, things change because we don't have that independence, right? Things depend on what happened the year before, the day before. And so, so we need more sophisticated methods to deal with that. We're going to kind of parking lot that, pretend that it's the same for now, but just be aware that that's what we would need to do. Okay, so what if we use this this data, this blue data, which is up to, it looks around 1945, right? So war happened here, and then and then there's this nonlinear relationship, right? And then we're back to a linear relationship. So we've got this strong linear, negative linear relationship. And what if we use this model to predict a value for here? This would be my prediction. But where would I actually be? Let's see here. And this would be the actual, right? So I'm way under predicting using this line. So you'd want to make sure that you are only making predictions for the values of X that you've built your line on. Okay. Okay. So, sorry, there. Oh, that's the output I want to bring in later. So first thing, we want to talk about R squared. Now, R squared is usually how we evaluate the fit of a line. Okay, and so usually how we evaluate the fit of a line. We've heard goodness of fit for chi-squared, but we could say goodness of fit for the line as well, mostly because it's fun to say, but or funny to say maybe. But it's usually how we evaluate the fit. How strong of a fit, how good of a fit do I have? And so the R squared is almost as important as the equation of the line when you're reporting a regression. You could have an equation, but unless you tell me how well it fits, right, that doesn't mean anything, right? So if we report a linear model, we must also report how well it fits. Kind of writing on top of myself here. Okay. So the R squared is the easiest way to do that. There are lots of other methods that we could use, but we're going to focus on R squared. It's the most commonly used. And I think even in Excel, when you add a linear regression, it just puts the R squared on there. And so pretty typical stuff that we use the R squared. And what we need is we need to know what the R squared is. Okay. And so R squared tells us what percentage of variability in Y is explained by the least squares regression line on the explanatory variable, which is your X. Okay. And so that's a long blurb and you should memorize it. Okay. It's the percentage or the proportion of variability of in Y that's explained by the least squares regression line on X. Okay. But to help you out in the beginning, because I know that's a lot, right? As soon as you see percentage of variability or proportion of variability, then I want your mind to go R squared, right? And so here, as soon as you see this, then you're going to say R squared in your mind. Oops. Think R squared. Okay, good. So we understand that the line that we fit is not going to capture all the activity, right? Unless that activity is exactly on the line, then it's impossible, right? So R squared tells us what percentage of that activity has been captured, okay, by this line. So some typical output that we get, and I added this, so I'm going to just copy. It's going to look like this. Okay. So it's using the same data set, slightly different variables. Okay. But what we want to do here is we're asked to predict annual murders per million, yikes, from the percentage living in poverty in a random sample of 20 metropolitan areas. Okay, so just noticing, okay, so this is a typical layout of our regression output. Okay, so here we have some regression output. Just going through here, we've got the intercept, and then we have the x variable, which means that these estimates, these are the coefficients. These are the coefficients of the model. Okay, so here, I'm gonna maybe focus on this and blow this up here. Copy, paste. Oops. Draw over some of the output. That's not very nice or not very good. There. So here we have the estimates or the coefficients. This is the intercept, and this is your x variable. Whatever. Variable. That's really all we need right now. Okay, so to build this model, what do we have? Well, we need an intercept and we need the slope. The slope is attached to the x variable, right? And so what we can do is we can just read this output and we can write the linear model as y hat equals b0 plus b1x, just generically, right? But our y, remember our y is, and maybe I'll use orange instead. This is our y variable, and the percent in poverty is our x variable. Right? Just looking at my graph, looking at the x-axis, looking at the y-axis, that's the easiest way to do it. And what am I expecting to see? I'm expecting to see this relatively strong linear relationship, maybe fitted something like that. Okay, and so the software, so R has done this for us. Okay, created this output. In fact, I'm going to remove that line because otherwise it might get confusing. So what we do is, okay, so then if we call y our murders, we can write this out as the murders hat. That's just saying the predicted murders, and of course units and whatever, but we want some shorthand name for it. So the predicted murders is going to be negative 29.901 plus 2.559 times the poverty percent. Okay. So we take, let me see if I can find a different color here. I've used them all up. How about this one? Take this, put it there, put her there. And then I take this and I put that there. And then going back to my usual colors, I take this, put it there. So now I can use this to predict the murders, the annual murders per million, okay, using some poverty percentage. Okay, so, and I don't think there's one in here. I do want to go through these questions, especially the last one, because I realize I forgot to mention it. But R squared, right, is just the correlation squared. And I know it's in here because R squared is calculated as the square of the correlation coefficient, which is your R, which means that you can go back and forth between the two, right? Remember, the correlation coefficient goes between -1 and 1. So if you're going from R squared to the correlation, you have to keep that in mind if you have a negative relationship. Maybe I'll add that because that's pretty important. but I'll do it when we calculate it together. Okay, so we can build this model, not bad, right? And so now, for example, what is, so a question would say, what is the predicted annual murders per million, for an area with, let's say, 19% in poverty. Okay. You want to make sure that your percentages, if you have 19%, you want to make sure that the units match. Okay, so one quick way that you can do that is to look at, okay, what are the units on the x-axis? It looks like it is in percent. So I can just plug in 19 here. So that's going to be require a little bit of legwork, right? Make sure that if you have a percentage, are you allowed to plug it in, right? And then make sure you use the correct units. Okay, that's usually what trips people up. So then if I have to predict the murders, then I have negative 29.901 plus 2.559 times 19. I can do that calculation. Make sure you follow order of operations, right? 2.559 times 19, and then add the intercept, which is actually subtracting in this case. 2.559 times 19. I'm going to show the steps. Of course, you don't have to, but it's nice to do it. 48.621 minus 29.901. 18.72. Okay. Which, if we look here and we have, 19 here maybe, then our line would probably go somewhere like this. And we predicted 18.72. Looks about right, right? We can draw this line, but it would look something like that. Okay. Of course, I don't have the right scale, so it's hard to say. Good. So that's how we use the line, right? And so we use it to predict future values. And you always want to first, before you go ahead and just plug things in, plug X's into your model, then what you want to do is you just want to check, okay, is it sort of within this range? Now we can go a little bit beyond, as long as we feel like there would be a linear model that would continue here if we collected more data, right? But we should restrict our predictions to about 14 to 26% in poverty, okay, for this model. Okay. And so if we had to interpret the intercept, okay, and then interpret the slope, and I find it's easier to write with the big pen, but I know it's easier to read with the little one. But so for the intercept, I think it's the intercept first. The intercept is negative 29.901. Okay, and so that is what? It's the predicted annual murders per million if the percentage in poverty is 0, right? That's not meaningful because there will never be 0% in poverty, unfortunately, right? And so that's never going to happen. We don't expect that to happen. We hope for it to happen, but we don't expect it to happen. Okay, and so the predicted annual murders per million is negative 29.901 if the percent in poverty is 0. And then I'm going to follow it up with, okay, this is an extrapolation. So this is not meaningful, right? It's not useful information. A predicted negative annual murders per million, that doesn't exist, right? We can't have that. You can't unmurder someone. And so you hit 0 and then you're done. Okay, so, but that's the predicted annual murders per million if the percentage in poverty is 0. So this is not meaningful since it is an extrapolation. And we do not expect to see an area with 0% in poverty. Just based off of the data, it looks like it ranges from a low of about 14 to a high of 26. So that's what we're expecting to see. Okay, how about the slope? If we have to interpret the slope, how do we do that? So for the slope then, the slope is 22.559. Okay, so for each unit increase in X, which in this case is the percent in poverty, then we expect to see a 2.559 increase, because it's positive, in the predicted annual murders per million. Okay, notice how I'm just taking the definition, that general definition, and I'm plugging in the values that I have and the variables that I have. Okay. So the predicted annual murders per million. Oh my gosh. I usually do the slope and then the intercept, and I guess I got caught on autopilot. Sorry, delete that. Delete it all. Well, okay, so we only have the tools for linear models, and most of the time, the linear model will apply. Even if you have a non-linear model, you would do a transformation to make it linear. So then the interpretation becomes a little bit tricky because, yeah, you've taken the log, or maybe you've squared a value, right, to capture some curvature. But for something like this, this is linear. So it's best described by a linear model. But yeah, so if you have a non-linear model, ultimately what happens is you force it to be linear, and then you just apply the same method that we're doing here. So it's good, because then you already know what to do. You don't know how to do it yet, but you know what to do. So it's good if it happens. So you'd have to play around with it. Usually what you would do if you're taking the log, for example, is you would look at the histogram of each of the X and the Y's, and then whichever one is skewed, that's the one that you would manipulate, because if both of them are normal, then you're going to have a linear graph. Okay, so it's the one that's skewed that you want to manipulate to make it normal, and then you'll have a linear regression. But cool. So for the slope here, let me try this again. Slope, Emily, slope. I usually do slope and then the intercept. It's no reason to trip up. But here we go. For each unit increase in percent in poverty, notice how I just replaced the generic X by what the actual variable is. We expect to see a 2.559 unit increase in the predicted annual murders per million. Should have picked a more fun example. Pretty sure there's a cat example in there that I could have chosen, but I didn't do it. The predicted annual murders per million. Nice. Okay. So we also have the R squared. Now the R squared is typically reported as a decimal, but it is a percentage. And so here the R squared is 70.52. Okay. So we do have this R squared adjusted. The adjusted R squared doesn't really come into play until we have more than one X variable. Okay, so if we have time, I'm going to show you what happens if you have more than one predictor, which we can do. It's called multiple linear regression. And we interpret things the same way. And we're going to have an R squared, but then we would use the adjusted R squared because we should be penalized for adding more predictors, right? Because you don't want to overfit your model, but that's like another course. Okay, so so our R squared in this case is 70.52%. So we're going to interpret that in terms of this data here. R squared is 70.52%. Okay. And so remember, R squared is the proportion or the percentage of variability in Y that's explained by the least squares regression line on X. So now all I'm going to do is I'm going to take out those generic references and put in my data references. Okay. And so what it says is the interpretation of R squared in this case is 70.52% of the variability, variability in annual murders per million explained by the least squares regression line, explained by the least squares regression line, on percentage in poverty. Oh, is explained there. Otherwise it doesn't make sense. Okay. And so notice here the percentage in variability or the percentage of the variability, and then you can kind of stop reading, because if you see that some percentage or proportion of variability, your mind should go R squared. Okay. If you're interpreting R squared, then you can look at the definition of R squared and you can just rewrite the definition as a statement. Okay. Okay. So the R squared, I guess I could have labeled this A, B, C, D, E. So we want to calculate the correlation coefficient. And so what I'll make a note of here is that r squared is just the lowercase r squared, which is the correlation. Correlation coefficient, but usually we just call it the correlation. So if I have r squared, one thing that we need to make sure of is that we convert it to a decimal first, right? Whenever we're using percentages in math calculations, we have to use the decimal version, right? And so it's very rarely the case that we can use just the straight percentage. I can only think of one where I've seen it, and that's the rule of 72 in business math. Doesn't matter. R squared need to convert to decimal before doing calculations. Okay. So we have r squared, which is 0.7052 equals, and I'm going to say the correlation squared. Yeah, exactly. The rule of 72. It's how long, approximately how long is it going to take to double any investment? It's a fun rule, but yeah, that's the only time that you would use the percentage that I have come across. Otherwise, you always convert it to a decimal. Okay, so to find the correlation, all we need to do is to take the square root of both sides, right? So if I take the square root here, but remember, and it's often that we forget, right? But when I take the square root, I actually end up with the positive version and the negative version, and then we need to select which one is appropriate. Okay, and so the root of 0.7052 is the correlation. Okay. And so here, the sign will depend on the relationship. You've got two tools to check. We have a positive slope in our regression equation, so we know it's going to be positive, but also we have the scatter plot and we see a positive relationship here. Okay, so I'll do this. We can check, first check the slope. Since our slope is positive, remember the correlation tells us the strength and the direction of the relationship, right? And the slope is the relationship. And so if it's positive, then the correlation must be positive. So since our slope is positive, the correlation is also positive. Is also positive. And we can check the scatter plot. We see a positive relationship. So therefore, the correlation here is going to be the positive square root of 0.7052. So the square root of 0.7052 is going to be 0.839761871. I am not going to round it because why would I? But you would round to, so here I have 4 decimal places. You would keep at least 4 decimal places. Why not just keep it as it is? Okay, nice. So if I give you some output, you need to be able to construct the line, right? So construct the model and then interpret the slope, interpret the intercept, so interpret the R squared or potentially find the R squared, right? There's a flip-flop there. But then you would need to have the correlation, right? Then you can square the correlation to find the R squared, and then, but know the relationship between R squared and the correlation. Okay. So what I'm going to do is I'm going to add, there is this example where using the high school grads where we plug in the given information. Okay, so this is kind of as far as doing hand calculations as we're going to get. What I'm going to do is I'm going to add this to the end of our notes today. Okay, so we're not going to go through it. You are expected to do it for the assignment, but it's more important that you're able to read that output and interpret it and build your model and use it for predictions. Okay. So I'm going to leave that and put it at the end of these notes. Okay. Oh. The last few things that we want to talk about are, okay, once I've fit a line, then I need to, and I'll make a note here, see the end of these notes for a full example by hand. Yeah, given that information. But because I'm short on time here, I do want to just wrap up by talking about, okay, once I've fit a line, then how can I talk about how well it fits? We have the R squared, so that's good, right? So R squared tells us the percentage of variability the line captures, so that's good. And then what we can do to follow up on the R squared is we can do what we call a residual analysis. So a residual, remember, is the distance. It's so the residual is the E, which is the observed minus the predicted, right? So the residual is the actual minus the predicted. So what are we looking for? If we're doing a residual analysis, things that we're looking for are linearity, right? How is that linearity assumption working out for us? Did I assume I had a linear relationship when I didn't, right? That's bad. We want to fix that, right? So that would affect your R squared, but it's not until you see it that you know that that's why it's affecting your R squared. We're looking for nearly normal residuals, right? Which means that the lines are evenly scattered around, the points are evenly scattered around the line. We're also looking for constant variability. Now, the reason for that is because if we have non-constant variability, and I'll show you, maybe I'll bring in the example right now, is because, hey, where is it? Guess I don't have it. Let's bring in this. It's sort of in that last one. Okay. Okay. I wanted to talk about constant variability, but how about we just plug through the other ones first? They're a little bit more straightforward. And so the linearity assumption, these top graphs are the data scatter plots. Whereas these bottom ones are what we call the residual plots, the corresponding residual plots. So what we're going to have is, instead of having your response variable on the y-axis, you're actually going to have the residuals on the y-axis, and you're still going to have your x, and maybe I'll say explanatory variable here on your x-axis. So what we're going to look for, if we're looking for linearity, then we're going to be looking for random scatter around 0. Okay. So a residual plot plots the response, and what we're looking for is random scatter around 0. Notice that the residual plots, and I'm going to zoom in here, these residual plots, they're basically just magnifying what's going on in the actual plot, right? But here I'm looking for random scatter and it looks relatively random around 0. Whereas here, this is bad, right? It's magnifying that nonlinear relationship. So we shouldn't be fitting a straight line here, right? So we look and we see, okay, it just magnifies the curvature. And so this does not satisfy the linearity assumption. Okay. Now here, this is kind of a subtle case of non-constant variance. So we do have random scatter around 0, but it looks like there's less scatter, right? So they're more tight around the line here at the beginning for these values of x. And then as we go across the values of x, the line gets wider. Okay, so that's going to be what we're going to look at for the non-constant variance. So here at 0, we want random scatter around 0. If you have the residuals, how about this? If you're checking the normality of the residuals or nearly normal residuals, then, well, you can do a histogram, and yeah, so it's a relatively weak relationship here. And it is hard to see that there's non-constant variance, but I'll show you a more extreme example. But yeah, that would be a weak relationship. So for checking the normality of the residuals, again, they should be centered on 0, and you can use a QQ plot if you want. But usually it checks out. If you have random scatter around 0, then you usually have nearly normal residuals. Now, the constant variability for kind of an extreme case, if you have, and let's just do the response variable against the x variable, then if we have points, and then it just keeps getting wider and wider and wider. So if we get this kind of, then we fit our line, maybe like this. Okay, this would be non-constant variance, because here, right, we have very little variance. Very little variance. And here, right, for these values of x, right, I've got huge variance, right? And I've got increasing non-constant variance, large variance around the line. Now, the reason this is bad is because here in the very little variance section, we're going to be able to make great predictions, right? So here our predictions are really, really good, really, really strong. But then as we move out for other variables or for other values of x, larger values of x, then all of a sudden our predictions are not as reliable, right? And so here in this case, maybe I'll put this on the fresh page here. Down there. So in this case, as we move across increasing values of X, our predictions become less reliable, right? We don't have that constant reliability. Our predictions become less reliable. And there are things we can do to manipulate it. We can do transformations again to try to fix this, okay? Or you might have to break up your data, right? Break up your X and build different models for different values of X, okay? And so those are just some of the things that we can check. I'm not gonna get you to do it, but it's good to be aware that we have these checking mechanisms, especially if you hear residual plot, then it helps to know what that means. Okay. We have different types of outliers, but with my last 3 minutes, I know, I want you to read the section on the outliers on your own, and I want to just show you read the page on outliers. We have influential points, and the gist of it is if you have an outlier, what you do, you don't want to remove a point because that could be an interesting point that you want to capture. And it usually is. So you don't want to just remove it. But what you do is you remove it and you fit the line without it, and then you put it in and then you fit the line with it. And if the slope changes significantly, then you need to make a decision. If the slope isn't affected by the removal or having it in there, then you may as well include it, right? But just multiple regression or multiple linear regression just because there's one, the last question on the assignment, and I still want you to do it. But what happens is if we have more than one predictor, which is a value of X, right? Then we have multiple linear regression. But even without I'll skim the question here. So a survey of 55 Duke University students asked about their GPA, the number of hours they study at night, the number of nights they go out, and their gender. We can show this summary output here, okay? So what we have is we have the GPA, which we're trying to predict, is a function of 0.00 times the study week. Maybe I picked a bad one. Plus 0.01 times the sleep night. Still might not fit it on here. Plus 0.05 times the out, and minus 0.08 times the gender. Okay. So you can make predictions given inputs, right? And so here we can predict the GPA given inputs for each of these variables. And that's about as far as we'll go, obviously, because I'm all out of time. But the key thing about interpreting these coefficients now is that that's the increase in GPA or potentially decrease, holding all the other variables steady. Okay, it's just a little quick question on the assignment. And so I wanted you to see it so that it's not so scary. Okay, I guess that's the end of the material. I have so much more to say. Anyways, I know I'm all out of time, but it's important. Congratulations. That's the end of the material. So cram that last bit in, but so tomorrow, so tomorrow we're going to do just a final exam, just an overview, and hey, applause everyone. I'll say I got a standing ovation. So we'll talk about the final exam tomorrow, and then you're ready to fly on your own. All right. If you have any questions, let me know, but I'm going to stop this recording here, and I'll see you tomorrow.